Hello, my name is John Elliott, and thank you for attending today's webinar. I'm a security advisor at Jscrambler, and before that I worked at MasterCard. I was MasterCard's representative on the PCI Security Standards Council, actually on the committee developing this new version of PCI DSS. In today's webinar, we're going to take an in-depth look at e-commerce skimming and the new requirements in PCI DSS that aim to combat these attacks. I'm going to start off with a quick reminder of the PCI DSS version 4 timeline, and then we will take a look at the problem that the JavaScript related requirements in PCI DSS version 4 are designed to address. From there, we're going to look at the requirements themselves and then how Jscrambler's web page integrity product both meets the requirement of the standard, but more importantly can stop JavaScript skimming attacks. And then finally, we will also look at another way of stopping these attacks and achieving compliance with the new requirements in the standard by using web standards, content security policy, and sub-resource integrity. So firstly then, a reminder about PCI DSS version 4. It's the first major release of PCI DSS since version 3 came effective in, 2015. The standard is revised periodically, and that's to address both changes in how card payments work and changes in the way that criminals attack how card payments work. So the changes in the standard are quite large because, well, in the period between this version and the previous version being released, there's been a lot of new criminal activity that needs to be addressed. And the way we build technology now in 2022 is very different to how it was in 2015. So there are changes to existing requirements. There's a completely new way of doing validation called the customized approach. And there are 64 brand new PCI DSS requirements, 2 of which deal with e-commerce skimming attacks. And that's what this webinar is concerned with, those 2 new requirements. I want to quickly mention the timeline for implementing PCI DSS version 4. As I said, the standard was released earlier this year, and currently organizations can validate their compliance with either version 3.2.1 of the standard or version 4 of the standard. After the 1st of March 2024, you can only validate against version 4 of the standard, but that doesn't include about 51 of the new technological requirements, which only come into force after the 31st of March 2025. And the 2 new requirements we're going to talk about today fall into that category. This slide, I hope this summarizes the situation clearly. And the reason for pointing this out is to say that you've got a couple of years to work out how you're going to deal with this from a PCI perspective. Criminals are attacking e-commerce websites and stealing card data from them today. And so although the new requirements are not mandatory until 2025, when I was last responsible for a major e-commerce website, we had controls in place already to counter these attacks because we didn't want to be exposed to a skimming attack. Having said that, now let's look at how e-commerce skimming attacks work so we can understand how to defeat them. But before I do that, if you think this isn't a problem, then let me remind you of some of the major losses of cardholder data that there have been because of e-commerce skimming. Some of the most famous include British Airways and Ticketmaster, and there are many others, and if you Google e-commerce skimming attacks or major card attacks, you'll see those. These attacks exist because the web changed from being a static environment that just displayed, well, text and pictures, to an interactive one based around the JavaScript programming language. And that language is interpreted in every single browser. JavaScript's what allows, well, Gmail and basically everything else to act as fully interactive applications, and now why we see single-page applications. So if we take a very quick look at how the web works, and I'm sorry if this is like a revision for everyone, but I'll just be quick about this. So when your browser visits a merchant's website, it says to the merchant's web server, hey, can I have a page? And the web server is going to respond with everything that's needed to make a page, and that's going to consist of some HTML, a cascading style sheet, some text, some graphics, and some JavaScript. Your browser, whether that's Edge or Chrome or Safari, will take all of that content and render it to make a web page. Typically then, more interactivity wants to be added to the page, and so the browser is instructed to request more JavaScript from the merchant, which could be from the same web server or from maybe another web server in the merchant's control. And then the next step is normally for the browser to request JavaScript from various third parties. This could be for performance analytics, A/B testing, or just generic JavaScript libraries that are used to make the page interactive. Very typically, web pages will also contain some JavaScript relating to what's called a tag manager. A tag manager controls what third-party scripts are deployed onto a page for interactive advertising, tracking, and profiling. So the web browser will go off and request the JavaScript from the tag manager. And then having got that JavaScript from the tag manager, it'll be instructed by the tag manager to load lots more JavaScript from many more third parties. You can think of a tag manager as a way of the digital marketing department being able to control what third-party JavaScript renders on a page. And that typically relates to business partner transactions that are loaded into that web page. So if we pause briefly here, we can see that a web page consists of the content items that typically come from a merchant's own web server, and then lots of JavaScript from the merchant's website, from various third parties, from a tag manager, and from all the third parties specified in the tag manager. But here, we're not dealing with just a general web page. We're dealing with an e-commerce website, so we need to enable some payment functionality. And the merchant will typically do this by loading a bundle of JavaScript from a payment service provider, or from an acquirer, or from an e-commerce payment gateway. Whatever you call it, that's the entity that's going to help the merchant process the payment and submit it to the card networks. Today, I'm going to call that entity a payment service provider, or PSP. And typically, to generate the payment page, the browser will request some JavaScript from the payment service provider. And the JavaScript that comes from the payment service provider creates that payment form. The customer now enters their payment card information into the form, presses a submit button, and the data is sent to the payment processor. And what I've shown here is typically the way that most e-commerce shopping platforms work. So now let's look at the attack. The attack's very simple. It's based on the criminal being able to get their own JavaScript executing in the customer's browser. Once the criminal's JavaScript has been loaded, it's able to access all of the elements on the page, including the form entry elements that are going to be used to receive cardholder data. As the consumer types in their card data, the criminal's JavaScript reads it. When the consumer presses the submit button to confirm the transaction, the data is sent to the payment processor just as normal, but it's also sent to the criminal server. So at the end of the attack, both the payment processor has the cardholder data, and so's the criminal. The transaction happens as normal. There's no error produced, nothing for the customer or the merchant to see, which is what makes this attack hard to detect. And it's currently the way that most cardholder data is stolen by criminals. Also, because chip and pin or EMV has rolled out throughout the world, making attacks against in-store, brick and mortar, face-to-face transactions, that's effectively been made useless by EMV. So criminals have stepped up their game to attack e-commerce much more than they ever used to. Now, you may be wondering how the criminal gets their JavaScript to load in the consumer's browser. So let's look at the attack surface. Remember, all the criminal needs to do is to get the consumer browser to load their raw JavaScript. So they need to attack any of the locations from where the browser loads JavaScript. If the criminal gained access to the merchant's own web servers, they could either edit the JavaScript on the criminal's web server or insert a command to load their own criminal JavaScript. And that's how the attack against British Airways was carried out. The criminal could also tamper with JavaScript that's loaded from any of the third parties, and that's how the attack against Ticketmaster was carried out. The criminals attacked the chat provider. The JavaScript that operated the chat window was loaded from the chat provider's server into the payment page. So the criminal's JavaScript had access to all the data typed into the payment form. This was a targeted attack. The third-party chat provider was deliberately targeted by the criminals because they knew it would give them access to the cardholder data of Ticketmaster's customers. The criminal could also attack the tag manager. They could either add their criminal JavaScript to the tag manager itself, or to any of the locations typically specified by tag managers where JavaScripts can be loaded from. And that's how the Avaline breach happened. Of course, the great thing with attacking a tag manager, or JavaScript that's included by a tag manager, is the criminal can attack many sites at the same time. So these are typically random rather than specifically targeted attacks like Ticketmaster. The criminal doesn't know which website is going to load their script, so it'll include code that recognizes which payment provider or payment processor's forms being loaded, so it can then skim the data from the payment fields. Okay. Now we understand how the attack works, we should be able to understand how to stop it. what we need to do is to validate the integrity of every script that's running in the page, either when it's being loaded for the first time or when it's been added to the page. And then we also need to monitor if a script changes to detect if what we thought was a good script becomes a malicious script. When a script is added to a page, you need to understand what that script does and particularly what functionality there is in the script. For example, is there functionality in the script that gives it the capability to read fields or to tamper with form events such as a form submit or a tabbing out of a field? To minimize the attack surface, you should verify whether a script needs to be on the payment page. And if it does, validate that you're happy with the PCI DSS compliance status of where that script's loaded from. Because, as we've discovered, that script can affect the security of cardholder data. And even under version 3, the current version of PCI DSS, that means the location the script's loaded from and how that script's managed really does fall into a merchant's PCI DSS scope. And then when a script you've already authorized to be on the payment page changes, you need to be sure that the change is an intended and authorized change rather than an unauthorized change. So each time a script changes, you need to work out if the script has gained any new functionality that's malicious, either because the script has been tampered with by a criminal or because the third party isn't as trustworthy as you thought it was. And there's been a lot of cases recently where third-party scripts were taking a lot more data out of form fields than people intended that they should have done. And so to do this, you have to work out whether any new functionality is being able to read form fields or, again, hook into submit events, which means looking at the script. And as I'm sure you can realize, the only place you can make these decisions is actually in the consumer browser itself, because that's the only place you have all the JavaScript that comes together to make up a page. When I started in this industry, everything that went into a consumer browser came from my own web server, so file integrity monitoring on my web server was sufficient to know if there'd been any changes to any of the content that I was going to push to my customers' browsers. Now, because content comes from all over the internet and is assembled and rendered in real time in the browser, the only place to look for an attack is in the browser. To stop these attacks, version 4 of PCI DSS has introduced 2 new requirements. The first, requirement 6.4.3, is intended to manage and reduce the attack surface. It falls into the identify and protect domains of the NIST cybersecurity framework. You can see the requirement as it is written on screen, but basically it asks for these 4 things: that there's an inventory for every script on the page, that the inclusion of the script is authorized, that the script present on the page is necessary for a payment transaction, and finally that the integrity of the script has been validated. Let's look at each of these 4 things in a bit more detail. Firstly, that an inventory of all JavaScript on the payment page needs to be maintained. For me, this means that you need to record the URI of the script, when it was added to the payment page, and when it was removed. And you should probably have some information about which version of the script is present in the page. And from the perspective of being assessed by an assessor, I'd probably want to retain this information for, 12 months? Secondly, a script needs to be authorized. Now, the guidance says by management, but that's not part of the requirement. So you'd want to record who authorized it and when they authorized it. From an organizational perspective, you need to decide whether scripts need to be authorized before they're added to the page, or perhaps within a certain time period after you've detected a new script being added to the page. The standard doesn't make this clear. It just says that all scripts have to be authorized. And so I guess depending on your organizational workflow, you might have a process that authorizes a script to be added to a page before it's actually added to the page. Or if there are lots of departments that are responsible for adding JavaScript to pages, which is not a great thing, it's added to the inventory and authorized in a timely period. A written justification needs to be maintained of why that script is necessary for the functionality of the payment page. Although it's a separate requirement, I suspect this would happen at the same time as authorization. The reason for adding this requirement was to make sure that scripts added to the payment page was done so knowingly. And so by adding only necessary scripts, organizations would minimize the attack surface. In the forensic investigation reports that the card brands receive, it's quite usual to see that the scripts that were included on the payment page are basically the same as all the other scripts on every other single page on the website, most of which are completely unnecessary and not even used on the payment page. So the idea is that by reducing the number of scripts on the payment page, the attack surface is reduced. Finally, the integrity of every script needs to be validated. And again, the standard is not specific about what it means by this. For me, integrity means that you need to be sure that the script is doing what you think it does. In other words, that it hasn't been tampered with and that the functionality in the script doesn't have any malicious behavior. You also need to understand how you'll be able to validate that on an ongoing basis, because the second new requirement in PCI DSS version 4 is about detecting changes to scripts that have been authorized and already deployed onto the payment page. That other requirement's on screen now, and it's requirement 11.6.1. What's required is a change and tamper detect mechanism that looks for changes in scripts and HTTP headers. And again, you can see the requirement as it's written here. But for me, there are again 4 distinct parts of the requirement, which are this: that the change and tamper detect mechanism checks for changes to active page content, such as scripts, and to the HTTP headers. That it does this at least every 7 days, or another time period that you've defined. And that when it does notice an unauthorized change, that it produces an alert. Okay, let's look at those individually again. Firstly then, the change detection mechanism needs to check for changes in active page content. So that's going to be changes to JavaScript for most people, but it could be something else if that active page content allows access to cardholder data. It also needs to look for changes to HTTP headers. Now, for those of you that are not familiar with HTTP headers, these are typically defined outside of the markup of the page. They're set in the web server configuration and uses one of the directives called Content Security Policy. They can specify where JavaScript can be loaded from and where data can be posted to. And the reason for having this requirement in the standard is that if part of your defense strategy is to limit the location that scripts can be loaded from using Content Security Policy, a criminal's also going to have to change the HTTP header to make their attack effective. So that's hard to say. So an unauthorized change to the HTTP headers is an indication of criminal attack. The check for changes needs to be run at least every 7 days. Now, there are going to be a number of different ways of checking for changes. You could do it by using an external scan of the website using something like synthetic user monitoring, in which case you probably don't have the capability to do that every single day, which is why the standard gives that 7 days flexibility. As well as specifying a minimum of 7 days, the standard allows you to do a targeted risk assessment to work out the best period for your organization. That targeted risk assessment is a new thing in PCI DSS version 4. And by doing that, it doesn't necessarily mean that you'll have a longer period than 7 days. On a high traffic website that's taking a lot of transactions, I'd suggest that the targeted risk assessment could actually determine you do it more frequently than every 7 days. I also want to just pause here to mention that in about 5 minutes' time, I'm going to argue that you should be doing this in real time, which will give a much smaller window of compromise if there was an attack. Finally, the last thing in 11.6.1 is that an alert needs to be produced when a change to the page content or to the HTTP headers is detected. The standard's completely vague about what type of alert. It doesn't say how the alert has to be produced, but what it does say is that it has to be responded to in accordance with your incident response plan, which is defined in PCI DSS Requirement 12.10.5. So, together, the 2 new requirements basically demand the continuous assurance of integrity of JavaScript on the payment page, that all JavaScript is managed and authorized before it's added to the payment page, and that its integrity is constantly checked while it's on the payment page. I keep using that phrase, payment page, and it's a defined term in the standard. Here's the definition. It's a web-based user interface containing one or more form elements intended to capture account data. And that might be displayed as a single document or instance. It might be a document or component displayed using an inline frame, an iframe, Or it might be multiple fields containing separate iframes, which is the way that most payment service providers or PSPs work now. So you see, what's highlighted in blue here is the payment page. And what's highlighted in the pink colour is not a payment page. It's what I call the parent page of the payment page, the page that hosts the payment page in an iframe. And this is actually important because, as we know, in PCI terms, the way that the payment page is rendered defines which SAQ an entity is allowed to use. Because if the entity doesn't store, process or transmit cardholder data and has no responsibility for the form that collects the payment card data, that can dramatically reduce the scope that the PCI DSS requirements apply to, and therefore the number of PCI DSS requirements that are needed. So typically, where the merchant controls the production of the payment page, either because they define the form fields themselves or they load JavaScript that defines the form fields, but they post the data directly to the service provider, that's going to mean they're using SAQ A EP. But if they receive the payment data back on their own web server, then all the requirements in PCI DSS apply, so that's going to be SAQ-D or a full report on compliance. However, if they host the payment page in an iframe or use hosted fields, that's those multiple iframes, each containing a separate field to collect the payment card data, then the payment service provider is responsible for the generation of the page and the acceptance of the cardholder data, meaning the attack surface is very small. So the entity can take advantage of SAQ-A. And as you may know, SAQ-A has very few requirements. And because of the same origin policy, JavaScript running in the parent page can't access the contents of the payment fields running in an iframe. Yeah, but there have been increasingly more clever criminal attacks against iframed payment pages, with overlay attacks and attacks that are attacker in the middle type of attacks. And so, I guess to preempt criminals working out new ways of attacking iframes, the PCI SSC has added these two new anti-skimming requirements to the parent page as well as to the payment page. So requirement 6.4.3 applies to the parent page and even a page that just contains the URL for a redirection. For 11.6.1, the requirement applies to anyone that's loading an iframe or to hosted fields. So let's look at the compliance responsibilities associated with SAQs now. If you're using SAQ-A, you know the payment service provider's got to comply with these new requirements for the payment page. That's the bits in blue. But the merchant will also need to comply for the parent page that hosts the iframe, because typically they'll be loading a JavaScript bundle from the payment service provider to generate and request the contents of the iframe. Okay, so we've discovered how e-commerce skimming attacks work, and we've met what PCI DSS has decided to try to do to fix it. I guess I just want to quickly revise, is this still a real problem? Because if you remember the attack surface, the criminal just needs to get their criminal JavaScript by attacking one of 4 different locations: the merchant's own websites, any third parties from where JavaScript is loaded, the tag manager, and then any JavaScript libraries that are loaded in the tag manager, effectively from fourth parties. At Jscrambler, we look at lots of websites and lots of JavaScript, sort of what we do. And on an average site, we find that there are going to be about 35 separately loaded JavaScript components. And of that 35, about on average, around 70% come from third parties. So yes, most of the internet has a pretty large attack surface. I honestly think people don't understand this. Okay, having discovered the problem and the PCI DSS requirements designed to address the problem, I now briefly want to talk about what Jscrambler's web page integrity does. Web page integrity is powered by a JavaScript agent. That's the first agent that needs to be loaded into the consumer browser. That agent is protected by patented technology that's been used by Jscrambler and many of our customers, including banks, for several years. What web page integrity does is it effectively intercepts every single other JavaScript call made in the browser. So effectively, you can think of it as a software sandbox. From now on, when any other JavaScript does anything, it does it through the Jscrambler web page integrity agent. First of all then, that means the agent can report an inventory of all the JavaScript running in the web page. By looking at what the JavaScript does, it can then report on its behaviors. For example, is some JavaScript trying to access form fields? Is it trying to post data somewhere else? So Jscrambler can give you a guarantee of the integrity of any piece of JavaScript. But the agent doesn't just report what's happening. It can load rules, and those rules can specify what all other JavaScript on the page is allowed to do. Those rules can be applied to all script actions, and they can determine at a really granular level what a script can do, which of its behaviors are allowed, and what data fields it's permitted to have access to. But what's really powerful is that it can be set to block any malicious activity, and any activity that doesn't comply with predefined rules. Now, I want to be really clear that automatically blocking malicious behavior is not a PCI DSS requirement. But if Jscrambler's web page integrity detects a script is accessing the contents of payment fields, and you've defined a rule, which I assume you would, that says only the payment service provider's JavaScript is allowed to access those payment data fields, then web page integrity will block that activity. And finally, web page integrity can obviously generate an alert when anything changes or a rule is applied. Basically, it gives you complete visibility and control of the JavaScript that's running in the consumer browser. Okay, now let's see how Jscrambler matches up to the new PCI DSS requirements. Remember that requirement 6.4.3 is all about identifying and protecting JavaScript and has got 4 main requirements, which are maintaining the inventory, that scripts are authorized, that the justification of necessity is recorded, and that you validate their integrity. In respect of the inventory, web page integrity generates an inventory in real time as it sees a new script or it detects a change in the inventory is updated. Within the inventory, you can say if a script is authorized or not authorized. If you say it's not authorized, it will be blocked. If you say it is authorized, it'll continue to run. You can also configure how soon this authorization needs to happen from when you see a new or a changed script. So, if you say that the authorization window is 0 days, new and changed scripts won't be allowed to run until they're authorized. If, on the other hand, you could say, well, as long as something authorized within, say, 3 or 4 days, then that's okay. You can determine that based on your organizational workflow and on your tolerance for risk. Within the inventory module, you can record the justification of why a script's necessary. And finally, in respect of requirement 6.4, Jscrambler's web page integrity does what its name suggests. It validates the integrity of a script. It looks at the functionality of a script, it looks at its behavior, and it can give you an assurance of integrity. Now, if we look at 11.6.1, the detecting changes requirement, remember the 4 key demands here are that the changes to active page content and HTTP headers are detected, that it's done every 7 days or within a specified period, and that an alert is produced. Web page integrity automatically detects any changes to a script. We're also working on providing a recommendation of whether a change can be safely authorized or not. For example, look, if you're using something like jQuery and you're using jQuery version 3.5, and then you change it to the next version of jQuery, well, and at Jscrambler we've seen that version of jQuery in lots of other places, we could suggest that that's probably a safe thing you could authorize. Changes to HTTP headers are detected. And although that requirement in DSS is really designed if you're using the content security policy to meet the requirement, a change to the HTTP header could actually block the Jscrambler agent from loading, and so it could impact the security of the web page. Now the periodicity requirement. Because the Jscrambler web page integrity agent is loaded in every single browser, every single time that your payment page is loaded, it detects changes in real time, not every 7 days. And then finally, of course, alerts can be sent by email. They appear in the Jscrambler dashboard and they can be posted to your scene. But what I really wanted to remind you is that Jscrambler goes above and beyond the PCI DSS requirements, because any script that accesses the payment form fields or which it hooks into that submit button will automatically be blocked. So let's summarize what we know about web page integrity. Once you've added the Jscrambler agent to your page, it creates a real-time inventory of all scripts on any web page. It looks at the behavior of those scripts and can be configured to block a new script or a change script until it's been approved, or just to give you an alert to tell you about the change. Most importantly, Once Jscrambler understands the structure of your payment page, it can block any malicious access to fields containing payment card data and prevent a skimming attack. Now, you don't actually have to buy any products to comply with these two new requirements in PCI DSS. The way the requirements are written, and this was intentional, they can be mostly fulfilled by using two of the built-in primitives of the web, which are content security policy and sub-resource integrity. Firstly then, content security policy, or CSP. That's a set of directives that are typically set in the HTTP header, but they could also be set in the web page itself. What CSP does is it defines the locations that JavaScript can be loaded from and also specifies the locations where data can be posted. This prevents malicious JavaScript that's not been defined in the CSP from being loaded and can stop data being sent to unauthorized destinations. Additionally, CSP can be configured to produce a report if a browser tries to load JavaScript from any location that's not defined. And if it's correctly configured, it really does make it hard for an attacker to get rogue JavaScript onto your web page. Unfortunately, CSP is quite easy to misconfigure, and a single misconfiguration can allow it to be bypassed. However, it is built into every web browser, and it's part of the web standards, so there's great advantage in that it is completely free to use. The second inherent capability that can be used to meet these new PCI DSS requirements is sub-resource integrity, or SRI. SRI forces the integrity of all JavaScript to be checked by the browser as it's loaded. In this case, when I say integrity, I mean a basic check to see if a script's changed from what you expect, not whether the JavaScript does or do not do something malicious. To use SRI, when you include a reference to load some JavaScript into a web page, you append to the load command the hash of the JavaScript file that's being loaded. When the browser loads that JavaScript, it compares the hash you provided with the hash it generates itself in the browser, and if the hashes don't match, the JavaScript does not run. So unlike content security policy, which can report errors, if the browser doesn't load some JavaScript because the hashes don't match, then the JavaScript just doesn't load. It fails silently in the consumer browser. So like CSP, SRI is built into the web standards. It's also completely free. So now let's look at requirement 6.4.3, that's the first of those two new requirements in PCI DSS, and see how we could meet this requirement using CSP and SRI. Okay, there's nothing to help us when it comes to creating an inventory, or authorizing scripts, or justifying the necessity of a script. All of these would be manual processes that you'd need to maintain in, I don't know, a spreadsheet or a change control system. To validate the integrity of a script, initially you'd have to manually check that the script wasn't malicious, but you could then generate an SRI hash for the script, which would ensure that if it was modified by a criminal, for example, or any other sort of attacker, then the script could not execute. When we come to requirement 11.6.1, SRI will detect changes in page scripts, but unfortunately neither CSP nor SRI will detect changes to HTTP headers. So to do that, you'd need some sort of external scan that would request the pages from your website, and that external scan could look for changes to content, but also to the HTTP headers. So that could be run every 7 days. CSP violations are reported in real time, but otherwise the external scan will be needed to run periodically to pick up HTTP header changes. And although CSP is going to report an alert when there's a CSP violation, there's nothing in the standard that's true for SRI. So if there's an SRI violation, you'd need an external scanner to be able to pick up changes to the script and produce an alert. Now, my view is that for smaller merchants, CSP and SRI may well be adequate, especially if the merchant really does reduce the attack surface by taking out all non-essential JavaScript from the payment page. However, the challenges with using CSP and SRI are really around the day-to-day management. As I said before, it's quite hard to do CSP well, and if you get it wrong, it's easy for an attacker to bypass. There's some good papers written about how that happens. But the main problem with CSP, which I guess is also its major advantage, is that any additions of JavaScript from new sources will also be needed to be added to the content security policy. So this might work for a workflow in an organization where you've got a formal process for adding any JavaScript to the page, rather than just, say, a marketing department enabling a new tag in a tag manager. And when it comes to changes to existing JavaScript, every time a script or a library is changed, you'd also need to generate a new SRI hash for that new version of the script, and then also edit the page to include that new hash value. And, when scripts change and are revised frequently, this could be a significant overhead. It's really important to remember that SRI fails silently. So if a script is changed and you haven't changed the hash, the script will just stop working, which may not be the behavior that the rest of your organization approves of. And this is especially so when the JavaScript you're loading is from your payment service provider. Because every time the PSP updates its JavaScript, and then that's loaded into the customer browser, you'll need to be informed of that change, be given the new hash value of that script, and then update your page to include that hash value. And if you don't do this, the PSP's JavaScript will fail to load, and you'll stop taking payments, which everyone in the organization, I guess, will generally regard as, well, a bad thing. And if we look at the problem from the other direction, if you're a payment service provider or an acquirer that provides JavaScript to merchants, so you're acting as a payment service provider, and that JavaScript generates the payment page in an iframe, because of that change to SAQ A, merchants will also need to be provided with an updated SRI hash every time you change your code, and then they will need to add that hash to the parent page that hosts the iframe. And of course, if they don't do this, the problem is that when they don't do this, the payment processing will fail. And that will be put down to be your fault and not their fault. Okay, we've nearly reached the end of this presentation on the two new requirements in PCI DSS 4 and e-commerce skimming attacks. So now it's time for the free stuff. Firstly, if you'd like a free inventory of all the JavaScript on your website, just ask us and we'll make one for you. Secondly, we've got a couple of white papers that describe the new requirements in some detail. It's got just about everything I talked about today. And also, of course, how Jscrambler meets them. Again, we've got one white paper for merchants and a second for payment service providers. Just ask and they'll be sent to you. And finally, if you'd like a demonstration of web page integrity, we'd love to show you how it works. And with that, we've reached the end of this presentation part of the webinar. Thank you.